In this episode, we're going to discuss activation energy. Activation energy is the minimum amount of energy required to start a reaction, since most reactants need convincing to form new bonds. And we can see here a boulder on the side of a mountain is a good example of where activation energy comes into releasing energy. A boulder with its heavy mass will sit there because it has inertia which wants to stay put because of the mass. And so it needs activation energy in the form of a push. And if we give it a push over the hill, the gravitational potential energy is released and the boulder goes rolling down the hill, smashing things. And as it smashes stuff, it releases energy. It turns it into heat. All right, so here we move on. We have an example of activation energy, and we're going to build up a hill and put a boulder on it with the construction of this DVD tower. With the DVD case tower in place, we'll give it a little activation energy in the form of a push, and the gravitational energy is released. And if we could measure the heat that is generated by all those impact, which is very small measurement on our scale. But now when we look at the graph of activation energy, we see that we have to, it may not be that a potential energy is sitting on the edge, but it has to be pushed up over a ridge, and so you have to give it that boost of energy. And in a chemical reaction, this looks like two reactants, like in gunpowder, you put them together, or in a match where you have phosphorus and chlorate, and then you add a little energy in the form of a spark, or in a match, you get friction, which adds energy, and then that allows the bonds to form, and in the meantime, they release a lot of energy. And you can see in slow motion the amount of energy I put in by the way I'm holding it and the push that I have to give it, which is quite immense. And so the activation energy starts the reaction, and the phosphorus and chlorate release a lot of energy at first, and then it eventually wears out all the chemicals. The chemical reactions have produced CO2, which is carbon dioxide, and carbon on the match. But now, after the chemicals have reacted and that reaction is completed, now we have a different one, which is the wood reacting with the oxygen in the air, and you have a combustion reaction, and it's self-sustaining. The heat from the combustion at the tip continues the process down the matchstick, and you better get rid of it before it burns you. So the activation energy, you break these large blocks like cellulose in the match, but also in gunpowder we can see it. And we have these large molecules, and we get to our first large molecule, which is sulfur, the one that smells like rotten eggs. Homemade charcoal, our very own homemade charcoal, we made that in our fire, and our very home purchased saltpeter. And we mixed them out, we measured them out, because you have to mix them like a recipe or they won't mix right. We crushed them down so they're nice and fine and they can get really close to each other. There's our finished products. We mixed them up, and we did this in the class, and we laid them out in a line, and we're going to add some activation energy in the form of a flame, and we start the reaction on one end, and it actually starts, and the energy is produced at the start, follows the line down, and provides activation energy for the next row or the next line, and we get a nice beautiful reaction. And luckily we have a vent hood, because that is a lot of product being released. And here's an interesting view of how this chemical activation releases the energy. This is how it looks frame by frame, and you can kind of see a graph of the energy released. And this takes us back to this image, this infographic. And here we added a flame, and we had the reactants, which was saltpeter, sulfur, and carbon. and then we added some energy, and the reaction produced carbon dioxide and the smoke that you saw, and there's actually ash on the piece of board where the reaction took place. And in our final demonstration, which I hope you'll participate in, we're going to go back to matches, but instead of providing activation energy through friction, we're going to add it through heat or through a flame. To do this, we're going to start by getting a match, and we're going to add tape to it so that the width is uniform along the length of the match, and so that it's the width of the match head. We're going to get a piece of foil. We're going to leave a tiny bit of the stick out of the foil, and then we're going to measure out a little bit extra. We'll cut out a rectangle, and then we roll it up, and we crimp one edge, the bottom edge, and so the match head needs to be able to come in and out without much friction. And then here we are adding heat via a flame. There's no friction, but the chemical reaction is going to activate, and you get the burst of flame. And this is activation energy, the minimum amount of energy required to start a reaction, since most reactants need convincing to form new bonds.